Hello, everyone. Welcome to this video on finite automata. By the end, you'll understand the differences between deterministic and non-deterministic finite automata, DFA and NFA, their formal definitions, and some examples. Let's dive in. Okay, now let's head to simple explanation and overview. First, finite automata are computational models used to design systems such as text search engines or traffic light controllers. Second, a DFA, or deterministic finite automaton, is like a one-way street. For a specific input, there's only one path from the current state to the next. Third, an NFA, or non-deterministic finite automaton, is more flexible. Multiple paths can exist for the same input, or the machine might not move at all. 4. Imagine DFA as choosing a single, strict route to reach your destination, while NFA give you multiple options, even shortcuts. 5. Both DFA and NFA recognize regular languages, which are sets of strings defined by specific patterns. 6. One key fact: every NFA can be converted into an equivalent DFA, but NFAs are often easier to construct initially. Okay, next, let's head to formal definition. 1. A DFA is defined as 5-tuple finite sets of states, input alphabet, transition function, initial state, set of final states. This is the formal definition of DFA. Second, an NFA shares the same 5-tuple structure, but its transition function differs, allowing multiple next states or no next state at all. This is the formal definition of NFA. Third, key differences include the presence of epsilon transition in NFA, which allowed state changes without consuming input. 4. In DFA, all transitions are deterministic. For any input symbol, there's exactly one possible next state. Now, I'm gonna give you some example of this to make it easier to understand. Number 1. Let's discuss a DFA example. Suppose we want to recognize strings starting with 0 from the alphabet. For input starting with 0, it transitions to a final state and continues. If the input starts with 1, it rejects the string. Get it? Okay, now, second, for an NFA example, consider recognizing strings where the fourth symbol from the end is 1. The NFA allows branching transitions to different states as it evaluates the input. And while it may seem complex, it's conceptually simpler to build than a DFA for the same pattern. Number 3. These examples highlight how DFA and NFA achieve similar results, though their mechanisms differ. Finite automata have several practical applications. DFA is used in lexical analysis during the compilation process, where it identifies tokens in source code. It also used for pattern matching, like checking if a string matches a specific format, such as email addresses. NFAs are conceptually useful for scenarios like regular expressions or pattern searches in text files. Here's a quick comparison of DFA and NFA. DFA: deterministic transitions, no epsilon transitions, one state at a time. NFA: non-deterministic transitions, allows epsilon transitions, multiple states can be active simultaneously. Number 2. DFA may require more states after converting an NFA, but both are equivalent in recognizing regular languages. In DFA, there is a concept of dead states, states where no valid input transitions lead to acceptance. For NFAs, the machine explores multiple paths. If at least one path reaches a final state, the input is accepted. This allows NFAs to process some inputs faster conceptually, though computational they are equivalent to DFAs. Let's add another DFA example, recognizing binary strings divisible by 3. The DFA has 3 states, representing remainders 0, 1, and 2. The transition depend on the input and update the remainder. Number 2. For NFA, consider strings containing AB as a substring. The NFA transitions freely until it encounters A, then looks for B. Once AB is found, the input is accepted. NFAs can be converted into DFAs using the subset construction method. Each state in the DFA represents a subset of states from the NFA. This process can increase the number of states exponentially. The resulting DFA is equivalent in recognizing the same language, though it might appear more complex. Why is DFA not considered less powerful than NFA? Because both recognize the same class of languages, regular languages. Is NFA faster? Well, it seems conceptually faster due to a parallel paths. Practical implementations usually convert NFAs to DFAs for simplicity. And that's it for DFA and NFA. We covered everything from their definitions to practical examples, and even some of their real-world applications. I hope this video helped clarify the differences between these two types of finite automata. Stay tuned for the next video, where we'll explore push-down automata, a fascinating topic that takes computational models to the next level with memory and stack-based operations. See you there!